This will be part of my talk in regard of 3-5 semiconductors, which we apply. Among those is multi-junction solar cells with the highest efficiencies, also solar fuels production, for example, CO2 reduction, and also for hydrogen production. We have world record values, always with partners, very good partners. Here's my team. The main team members, which you can see here, two young research groups of young Agnieszka Pawluk and Juliane Koch, and also strong collaborators with my team, Professor Jägermann, Professor Hoffmann, Erich Runge, Rainer Eichberger, Max Großmann, a very good PhD students in the theory group. So there's a lot of experimental theory exchange and also exchange with other very important partners and institutions. Among those is the Fraunhofer Institute of Solar Energy Systems with Frank Dimroth and co-workers, and Lisa, Jacob Lisa with Harry Edwater, and also at HZB with the Roel van der Kroon. So we have really valuable partners which you need for fulfilling such complex device structures, and also preparation and analysis. I will talk about this. So what you can see here, after a motivation, I will face exactly to these efficient direct solar fuels production device structures with where you need that I will explain suitable tandems and of course semiconductor materials. You need to have functional layers. I will explain this. And then I will get briefly to the point of the analysis. Very important is the in situ spectroscopy. And finally, I will also address the issue of costs of critical materials, which has already been done during this conference, for example, this morning. That's one of my two favorite slides. I always would like to show this. This lists the problems, the challenges with we are facing on this planet in the future. And this is already more than 20 years ago that Richard Smalley, Nobel laureate, has listed this. And in particular, if you look at all these points, they are still very topical. And the main point was to say that if we have enough and suitable renewable energy available, then we are more or less also addressing all the other points directly or indirectly. We have already seen and heard about the conjunction between energy and water, and it's easy to explain that then food and environment is also considered, and all the other points as well. So I think this is still a very important message, even though it's already more than 20 years ago old. And one of the big points, as we all know, is greenhouse gas emission and the problems which we have. One of the main point is, of course, that the content of CO2 in our atmosphere is rising in a very critical state. So right now at values at around 420 parts per million. And at the same time, a little delayed, as we all know, is also temperature rising on this planet, also towards a very critical state. So this is all very alarming and urgent. And as we also have already learned at this conference, the remedy is photovoltaics, which has started in space. And is then, this is my also second favorite slide. We also have already heard about this, the increase of the exponential growth of global solar PV capacity, which we build on this planet here on the logarithmic scale. And if we look at the past more than 30 years, and only look 10 more years from now, then we are already at values where we are more or less having enough supply for the whole planet. Yeah, as we learned today, we need to get to values in the range of, let's say, 60 to 70 terawatts. And just looking at this, so impressive. We needed until 2022 to get 1 terawatt, and then within 2 years we got another terawatt on top. And so this will continue. At least we can see at the end of this year, we will be in the range of 3 terawatts. And yeah, this is one impressive thing. The other impressive thing we also have already seen this morning is the price development. The prices, for example, just in less than 2 years have been cut by a half. And so this is also all highly impressive and very good to see. And it's really happening everywhere here in the vicinity of Dubai. 5 gigawatt, 1 gigawatt is in the range of a power plant, nuclear or coal or gas. So this is really very impressive in China and in India and in Egypt. You always, everywhere see this fantastic development. And also in Germany, we can see this here, a very big solar park with 0.6 gigawatts almost. And then, yeah, also in different sizes. Here in Pakistan, as one more example, they call it the Pakistan miracle, a kind of revolution. You have many, many small modules in different places. And then we also have the agri photovoltaics. Also for Morocco, there is this bright forecast towards the next years. And there is potential really for a lot of renewable energy, of course, in Morocco. And this, of course, would be yeah, also a fantastic contribution to the world. And there's still many more ideas, opportunities, and limits which we can look at. We have already heard about tandem structures, and I will also address this in my talk. For example, we have developed with partners the 4-junction cells. This reached so far 47.6%, so almost half of the solar radiation is converted into free energy. This is really amazing. This was a cell which we basically have suggested with my team in 2007. And then 7 years later, it has been realized with a 4-junction wafer-bonded cell. And it's still the champion solar cell device structure here, this 4-junction cell, with a potential to more than 50% efficiency. And there's tons of more ideas. Concentrator photovoltaics, for example, which makes a lot of sense with regard to material resources, and agri-photovoltaics, which you could realize with such concentrator systems in a perfect way, as you can see here by these sheeps. Agri-photovoltaics itself, it's really a fantastic application of photovoltaics, of solar cells, with additional land use and enough land to build enough photovoltaics for the supply of this planet. And there's even more idea. This is a bit future-like, as you can see here, for urban development. Also, this would make a lot of sense, as you can see here, as some science fiction examples, but it's not fiction, it's rather science. But still, there is a lot more to do. So we just talked about the provision of power generation, but regarding transport and storage and mobility and the system stabilization, we would need solar fuels at different places, for example, for air traffic and mobility in general, and a lot of other applications of technical gases, which we need either way in such a strategy, as you can see it here. We need to think in life cycles, and that's a point which I will address in different regards. And also for the hydrogen production, of course, which is a key pillar of our energy system. Either way, we need a lot of hydrogen, more than 100 million tons for different applications, and all fuels contain hydrogens, independently what kind of fuel or e-fuel we are talking about. And only a very small amount so far is really green. And this is, of course, a very important point. Then you could ask the question, why should we not only simply use an electrolyzer and couple it to a PV cell? This is a long discussion we could lead. There is many reasons back and forth, having different devices and connections, or just having one device, which has, of course, advantages, thermodynamical advantages, also with regard to the abundancy of highly precious materials. And I will show this again, like platinum, rhodium, ruthenium, and so on. The idea, of course, is also just in principle fascinating, to mimic the natural photosynthesis, to mimic nature, and also with regard to potential scalability of these materials, like we have it in photovoltaics. This also would be a great advantage, having such artificial leaves without wiring to the outside. We can just produce hydrogen with individual devices. And that's what I want to address briefly and to explain it. How does it work? And as you can see here, the idea is to have such a device. I will explain why we need a tandem, and facing at many different scientific challenges, like, for example, catalysis or nanostructures, or in general, the electrochemical processes, which we also would have at normal electrolyzers, charge carrier dynamics, and so on. So many different questions. Many of those we already answered. I'm sorry for this. Many of those we already addressed and partially answered in our recent review on this. So this is a long review facing exactly to the artificial photosynthesis. And here I would like briefly, in a nutshell, explain the different steps. So the first step is to provide enough chemical potential to split water. And what we can see here is the energy diagram of a semiconductor. And as soon as we shine light on it, we are splitting electrons and holes, generating electron-hole pairs. And this gives us free energy in the semiconductor by splitting the so-called Fermi levels. These are determined here by the chemical potentials of electrons and holes. This sounds for many a little abstract, but it is real. You can measure it just with a multimeter, or you can see it quantitatively with photoluminescence. So this is a real free energy which we have and store in the semiconductor. This is the first step which we need to do. Then we need to compare it to the energy, to the free energy, which we need to split water. This is the difference of the redox potentials for the different half reactions at water splitting. And then we need also the so-called overpotentials, which we can modify and reduce by catalysts. This is all a very long story, which I briefly explain here, but it's very important and impressive. You can read it very well in the book of Peter Würfel, the development of the Fermi level splitting and so on, physics of solar cells. Then if we do this all and do this all perfectly, in the ideal case, we see that just with one semiconductor, we can not exploit the solar spectrum appropriately. That's shown here. So we need such high band gaps that we can only absorb a very small portion of the solar spectrum. This is the bad news. But the good news is there is a solution, and the solution is called tandems. So what we need is a tandem structure. I'm sorry, what you can see here basically. And this gives us both the appropriate photovoltage as well as the exploitation of the solar spectrum. And then we need all the other ingredients which we also have to have in a good solar cell, in a tandem solar cell. So the diffusion length of the charge carriers needs to be larger than the penetration depth of the light, and so on. So it's really a long, each point which I'm showing here needs normally a longer explanation, but we need to separate the charge carriers into the appropriate directions, as you can see this here. Also something which we might discuss longer, then we need to have a tunnel junction, which you can see here. And here we have the isoenergetic recombination of charge carriers. And at the cathode and at the anode, finally, we can have the hydrogen and oxygen production. For this, we also need the stability, of course, of the interface, the photochemical stability. We need to have a high catalytic activity, so catalysts which are appropriate at these different electrodes here. And if we do all this perfectly, then as you can see here, we can get to really very impressive values, values close to 20% solar to hydrogen efficiency. And that's what I'm showing here. This is the champion device structure here. And with this, we reached really competitive values already, 19.3%. And this was not at the bull's eye of the band gap combination, so there is still space for improvement. For example, if we apply silicon as the bottom cell, as you can see here. And so this is still all under investigation. And the final point, of course, like always, what we do is how is about costs. And of course, among costs is the availability of materials with the resource efficiencies, which you can see here. Yeah, and this I want to address briefly. 3-5 semiconductors, as you can see here, open the window for the so-called band gap engineering. And that is what we basically can do. And this is fantastic. We have a lot of different device structures, not only those which I've already shown here, the champion solar to hydrogen conversion or solar to electric power conversion, also the CO2 reduction conversion to CO in this example, which we have published recently, also with already efficiencies here with 6%, which is here achieved with a 3-junction cell, since you need higher voltages at this device idea, a device structure for CO2 reduction. So where's the problem? We have so many solutions. one of the scientific problems is, of course, to understand interfaces. How does it look like? How is the buried interface? We know from different authors, the first one who said this was Herbert Krömer, the Nobel laureate 2000. The interface is the device, and that's absolutely true. The interface is indeed the device. And for this, we need to apply a lot of different methods. And as I told, one point is the in situ spectroscopy. This is a little busy. This is our experimental setup, but what I want to show also here, we combine surface science techniques and all other techniques combined with the preparation, state-of-the-art preparation by metal organic chemical vapor deposition with in situ reflection anisotropy spectroscopy. And this is an amazing technique since it can really see the atoms, the order of the atoms at the surface reconstruction and everything. And also in chemical difficult environments like in the gas phase or also in the liquid. So this is a really fantastic method. I cannot explain it, just showing you intuitively here some pictures. So these are certain surfaces of indium phosphide and aluminum indium phosphide adsorbed with water. And you can see the differences during adsorption and of the different surface reconstruction. This is a long story. I don't want to make it to explain this here, just explaining that this is one of the key elements to understand the preparation of interfaces. So that's I was explaining. Now I briefly want to explain also the issue of costs. So what we have seen is 435 semiconductors combined with silicon and also with germanium. We have fantastic developments, champion devices, very important device structures, which we use in every day, everywhere, telecommunication, in transistors, LEDs, lasers, sensors, etc. And of course, solar cells and artificial leaves I have already shown. And so these are basically the best scientific solution. So the question is, also what we also work on in a big project, it's called H2 Demo, funded by BMBF. We combine it with silicon with different strategies, nanowires, quantum world structures, etc. So where's the problem, you could ask? And the problem is, of course, critical elements. Critical elements we can see here, for example, are indium. Indium at a similar level as silver is. We also learned that silver is mandatory so far for silicon solar cells as well. And also other materials. Basically what we see, all devices, all device structures, everything has some criticality, critical materials involved. It's getting even more critical if we think about catalysts, which are very critical. So, and that's what we are addressing and facing in our new projects. It's called SustainMat, Sustainable Energy Materials. And what the final point is, we need to look in life cycle assessments. We need to think about reduce, reuse, recycling, and substituting critical materials. So we need to think in the whole value chain, with including reuse, remanufacturing, recycling, and also the costs we need to look and to think about. It's only euro or dollar, or is it energy, or is it greenhouse emission? And also transport, we learned already today, this morning, is also critical. So with this, Yeah, and our idea, which we are currently working on, from looking at a material flux analysis, the life cycle assessment towards a full cost calculation, involving all these difficult questions, which I was talking about. That's what we currently do in a kind of a cycle, in a life cycle, including, of course, resource and product database systems, artificial intelligence, and so on. We are looking this in a first step backwards by looking from a device structure backwards and then forward to see the material fluxes, etc., the whole cycle processes. And that's what we do in a large team right now, involving all kinds of interdisciplinary topics with colleagues from economy and material science, physicists, theorists, and chemists, and so on. Okay, and this was what I wanted to address in this talk. The conclusion is the solar energy conversion is very fascinating. Still many questions, incredible development, but also challenges. And among this, as one strategy is to use V5 and silicon material structures with very high performance. And we need to look critically at all these techno-economic points, which I have briefly addressed. So last but not least, I would like to advertise for all young scientists our fantastic QuantSol Summer School, which is still open for application, already running for more than 17 years. And it's an opportunity for all young scientists to learn more about solar energy conversion and all the application opportunities. And finally, of course, I would like to thank you for your attention. Many thanks again for inviting me here, all the different partners which we have, and of course for funding. Thank you.